nonlinear elliptic equations.
Okay, thank you very much. So today I wanted to discuss in detail the proof of the George's proof of the Helder continuity. So let me recapitulate. We said that nonlinear equations in divergence form come from several areas, and basically the most classical is a calculus of variations, where you have a functional f of gradient u. Right, you can think the two classical examples. Well, there are the P Laplacian, or there is the area integral. This is the area integral, and then there is the Dirichlet integral, and so on. So you want to minimize, you want to prescribe. You are given a domain omega. And let's say you are given boundary values. So you want to look at, we want to consider functions u of x in omega with prescribed boundary values. I'm sorry, I realized yesterday sitting in the back that I should stay above some line. So we are giving a domain omega, and we want to look at configurations u, right, from omega to r, right, u restricted to boundary of omega prescribed. Okay, and among all such u's, you want to find the one that minimizes the variational integral, right? So find u0 minimizer of E of u equal to the integral of, let's say, f of gradient u. Okay, and usually this is done. This can be done. It's not simple in general, but it can be done by setting the problem in the right functional space associated to this f and the behavior of this f. For instance, if gradient f of gradient u has some p growth at infinity, then you want functions whose derivatives are in LP, and so on. And so, but I don't want to enter into that. The fact is, in general, you can find a solution. Let's assume you have been able to find a solution u0, right? A solution, but in general, this solution is, as I said, in the functional space associated to the f. Like in the case of gradient u squared, what you do is you look at functions whose gradient is in L2, and then when you find your minimizer, all you know is that your gradient is in L2, right? And and so you want to show further regularity. And in order to do that, you look at the Euler-Lagrange equation, divergence of fj of gradient u equal to 0. And the first question you may ask is, how does it look like a second order equation? And if you want to see why does it look like a second order equation, what you do is you take the derivatives across. When you take the derivatives across, you get that this equation, at least formally, becomes Fij of gradient u dij of u equal to 0. Okay, and so at least formally, it looks like if you manage to prove that if the gradient of u is Helder continuous, then you are done, because you can use the linear theory, the Schauder estimate in the linear theory, and then you can go for as much regularity as you want. Let me also recall that to get this, for this equation to really live in the elliptic regularity theory, what you need is this to be a positive matrix. That is the standard hypothesis in the calculus of variations, that f is strictly convex. Okay? So you want to prove that gradient u is Helder continuous, and then what you do is according to this philosophy, that the equation is invariant under translations, has a comparison principle, so the gradient should satisfy something. So you compute the kind of equation for the directional derivative. And if you try to compute it here, you get third derivatives and something which is complicated. But if you compute it here, right, then you still get an equation with divergent structure, divergence of Fij of gradient u Dij of u alpha equal to 0. Okay? And so, as I said, that I think that the powerful idea of the Georgi was sort of to recognize that just by thinking of this as a matrix of elliptic coefficients with no regularity, right, that still will imply that u alpha was Helder continuous. Okay, so the Georgi's theorem in the calculus of variation appears not to show the regularity of the function, but to show the regularity of the first derivative, right? And says that. It says that if you have a solution u, so let u be a solution of the Aij of x, Dj of u equal to 0 in B1 of Rn, then u is C alpha in B1 half, and the C alpha norm of u B1 half is bounded by a constant that depends only on the ellipticity. All constants, if I don't specify, depend only on the ellipticity. Constant times the L2 norm of u in B1. Okay. And so I said last time the Georgi theory basically is divided in two parts. The first is the first part is an L2 L infinity lemma. So part 1 infinity says that if the L2 norm of u plus in the ball of radius 1 is small enough, then sup of u plus in B1 is smaller or equal than 1. And of course, since the problem is linear, I mean, the small enough doesn't mean anything because you can always divide u by delta times its integral to make it less than delta. Okay? As I said, this is the geometrical meaning of this first part. Is like saying in some sense that the graph of u cannot make spikes. In other words, you have here the graph of u in the ball of radius 1 and can be very wiggly because you don't know anything at this point, right? But you know that under u there is very tiny volume in the sense that the L2 norm is small, and then what you want to prove is that in the ball of radius 1 cannot make a spike. Okay, and so I gave an analogy last time of the Georgi's argument for minimal surfaces, which is sort of easier to see, right? That says, okay, the ball of radius 1, and suppose you have a minimal surface floating inside the ball, and you know that the volume down here is very small, then the minimal surface can never reach the ball of radius 1/2. Okay? And this was done by this, I think this is one of this beautiful idea that is that you take a sequence of rings, right? And you show that the area of, let's say, the smallest area, that is the smallest neck that the minimal surface has, decays along the rings fast enough to be completely strangled at the level, well, by the time you get to the level 1/2. Okay, and this is the same idea that the Georgi uses in in the proof of his first part. So, yeah. Pardon?
The second ball is smaller on the right. The suit pulls on it on 1/2.
Yes, sure. Yeah, thank you. Yeah. If you don't have to go strictly inside, life would be beautiful. Yes.
That's a set though. It's the suit of
On B1/2, yeah. I mean, maybe the notation is, yeah. Okay, so the main, so as I said, the proof is basically, the whole proof is based on the interplay between two conflicting inequalities in some sense. The first one is a Sobolev inequality that says that you can control by the L2 norm of the gradient the LP norm of U. So let W be supported in V1, then the LP norm of W in V1 is controlled by the L2 norm of gradient W in V1, right, for some P which is slightly bigger than 2. Okay, and if you are not ambitious, then you can do a simple proof by potential theory, right, because you can write, take the ball of radius 1, and you take any point and you write U and as this integral of UR along each line, right? And if you do that, then what you get is that you get that W of x0, right, is the integral of, you can write it in polar coordinates and then pass it to Euclidean coordinates, and what you get is this is like gradient W of y times x0 minus y over x0 minus y to the n dy. Okay. And this is a convolution with a function. Since you are in the ball of radius 1, infinity doesn't matter, so this is a convolution with a function, right, which is almost in ln over n minus 1, right? And so it's a convolution with a function which is something better than L1, so the convolution is in an LP better than L2. Okay, and if you want the exact embedding inequality, then it's the critical case of this, and you use another argument. But in principle, just by looking at this, you can say that there is this P that satisfies this inequality. Okay? So that's the Sobolev inequality. The important thing I want to point out about the Sobolev inequality is it is sort of a different homogeneity in some sense. I mean, it's all homogeneous of the right thing, but it's not 2, it's 2P, right? Which was the phenomena in the example of minimal surfaces where volume controls area, right, was in the example I gave yesterday, but area controls volume to the n minus 1 over n. Okay? So, so this is the Sobolev inequality. And then the energy inequality, right, that says that if inequality that says that if B is a subsolution, of of an equation Aij dij of B, I mean di Aij dj of B bigger or equal than 0, right? Then you multiply it by phi square V, let's say a non-negative solution. Let me put a non-negative solution here. I mean, it's general, but we'll work with non-negative solutions. So you multiply it by phi square V, and this is positive, and this is positive, so this is bigger or equal than 0. Okay. So yeah, di aij dj of v, this integral is bigger or equal than 0 because v, this is positive and this is positive, right? And so, so if you integrate by parts, you can put the di here. Okay, and to get the energy inequality, what I want to do is I want to pass this phi from here to here. Okay, and when you pass the phi from here to here, right, then you have an extra term that involves v, gradient v, and gradient phi. So you do the you just do the computations, which I won't do, and you get the energy inequality. That says that you will succeed in passing a phi from here to here. So you have the integral of gradient of phi v transpose aij gradient phi v, right? But you will have a leftover term. This is going to be smaller or equal than, so the standard thing you do is the integral of v squared times the sup of gradient phi square. Anywhere square. Times a constant. Okay. Unless I specify all the inequalities are up to a constant. Unless I said the number there is exactly 1, which I don't think I will ever say all the inequalities are up to a constant. Okay? So this is the energy inequality. The energy inequality is 2, 2. While the Sobolev inequality is 2p. Okay.
I'm sorry, why do you have a transpose there? Or what is that?
It's just a notation for phi ij, matrix vector vector. Okay, I mean, just
Sure, thanks.
yeah, it's the notation. Okay. Okay, so now let me show you the proof. If you remember the proof of the minimal surface sort of baby theorem consisted in taking dyadic rings, converging to the ball of radius 1/2, right, and obtaining an iterative inequality from ring to ring, okay, and was this funny nonlinear inequality that had an enormous factor in front, but was nonlinear, and that's what allowed for the things to disappear. So this is exactly what I'm going to do here. I'm going to consider first a family of cutoff. Okay? So these cutoffs are going to be, so I'm going to put here a sequence of phi k. Okay? And phi k is going to be identically 1 in the ball of radius be 1/2 plus 2 to the minus k. Okay, so let me do a little picture. Maybe I do the pictures on this side. So here I have the ball of radius 1, here I have the ball of radius 1/2, and I'm going to take this sequence of rings, 1/2, 1/4, 1/8, and so on. 1/2, 1/4, 1/8. Okay, and so phi k is going to change from 0 to 1 inside the ring. So it's going to be 0 here. It's going to change inside the ring from 0 to 1, right? Then it's going to be 0. So phi k is going to be identically 1 in the interior ball of the ring, and it's going to be identically 0 outside the exterior ball of the ring. Minus k minus 1, that is the previous ring. Okay. And then I'm forced to do the gradient will be of order 2 to the k. Okay. Let me point out that in the support of of phi k, phi k minus 1 is identically 1. Okay, so note is identically 1 in the support phi k. Okay, so I have this one and I have the previous one comes along here, and by the time it reaches the support of the next one has become identically 1, and so on. Okay, so I'm going to put these cutoffs in the energy inequality, right? And I'm going to cut the u, because the energy inequality is valid for subsolutions. So if I take the maximum between u and a constant, that's a subsolution. Okay, so I'm going to apply the energy inequality with these cutoffs to the functions uk, and uk are going to be u minus 1/2 minus 2 to the minus k plus. Okay, so in other words, I have here the graph of u, right? And what I'm going to do here is the level 1. And what I'm going to do is I'm going to cut diagonally approximating the level 1. So this will be the u1, and then the next one will be whatever is left inside here. I mean, this doesn't look like a graph of a function, but you know. So I'm cutting out all the different levels, okay? And the idea is to show that by the time I get to the ball of radius 1/2, uk has disappeared. I'm sorry, not 1 here. By the time I get to the ball of radius 1/2, uk has become identically 0. Okay, in other words, it has the part above 1 has disappeared. And so what I'm going to do now is the same as yesterday. I'm going to write an iterative inequality on the rings. Okay, so I want to control the L2 norm of uk plus 1 by the L2 norm of uk as yesterday. But I want to control it in this nonlinear fashion. Okay, so on one side, so of course we have to use, we go from uk to uk minus 1, we go from uk to gradient u by Sobolev, and then from gradient u to u by the energy inequality. Okay, so by Sobolev I have that the integral of gradient of phi k uk square, right, controls the LP norm. Okay, but I really want the L2 norm here. So here is where I have to exploit the fact that the homogeneity is not the same. So I'm going to say the L2 norm. So here I want to put the L2 norm. Okay, so I say the L2 norm I use Helder, right? I use Helder with phi k uk and with 1, that is with the indicator function of the support of this. Okay, so I get here, this is smaller or equal than the integral of phi k uk to the p to the 2 over p, right? Okay, just Helder, and then I get times the measure, then I get the integral of 1 to the conjugate exponent to the conjugate exponent in the inverse. So basically at the bottom line is that here I get the measure of the set where phi k uk is bigger than 0, that is the measure of the support of phi k uk to some power. Okay, because I have to integrate 1 and then I have to take 1, the conjugate exponent. Okay, and the important thing is p being bigger than 2, I get this little power. Okay. So if I plug it here, what I get, if I plug it here, what I get is, here I can replace by the in energy, but this stays, right? So I get, so let me call this quantity, this is a quantity on which I'm going to write the recurrence relation, so let me call this quantity AK, right? So what I get is that AK is smaller or equal than, here I replace by the energy integral, let me call it EK, but I have left over the measure the measure of the set where ik uk is bigger than 0 to the epsilon. Okay? Okay, now on EK, now I use energy inequality. Okay? And so,
Write EK to some power.
pardon?
Okay, the 2 over P.
No, because here I have 2 over P. I already normalize. You know, here I have to divide by 2, and then I will have 1 over P, and so on. Right? This is Sobolev. I have the 1/2 here, right? So the power is 1. Okay? Okay, this is Sobolev. I put the 2 all over, but this should be L2 norm, LP norm, and when I use Helder, LP norm, L2 norm. Right? This Helder is all homogeneous of degree 1. Everything is homogeneous of degree 1 at the end. Okay? Okay. So now EK energy inequality tells me that EK is smaller or equal than the integral of UK squared in the support of phi k, right? And have to multiply it by the gradient of phi k squared. So I get here something like 2 to the 2k. This is, as yesterday, a very bad power. Okay? Now I want to put this and this together, and I will get a power bigger than 1 of AK minus 1. So I want to convince you now that this plus this together will give me a power of AK minus 1 bigger than 1. Okay? So let me convince you of that. Okay, so here remember that on the support of phi k minus 1 was identically 1. And UK is less than UK minus 1 because I'm truncating at a smaller level, right? So that means that here I can replace this by 2 to the k, and here I can replace this by phi k minus 1 UK minus 1 squared. Okay? So I can replace this term by 2 to the 2k AK minus 1. This replaces this term. So let me erase here. And this replaces this term. Okay? And where phi k UK is bigger than 0, UK minus 1 is bigger than 2 to the minus k. Because if UK is positive, right, UK minus 1, right, was the truncation a little bit below, right? Remember I was cutting here and here. These are two consecutive levels. So if the function here is positive, the function minus this constant is positive, the function minus this constant is bigger than 2 to the minus k. So UK positive implies UK minus 1 bigger than 2 to the minus k, right? And phi k positive implies phi k minus 1 identically 1. Okay? Which means that this set is contained in the set where phi k minus 1 uk minus 1 is bigger than 2 to the minus k. Okay? So let me erase it, and I have that here. I can replace that by the set where phi k minus 1 uk minus 1 is bigger than 2 to the minus k. Okay? And by Chebyshev inequality, the measure of this set is smaller or equal than 2 to the 2k, the integral of phi k minus 1 uk minus 1 square. That is 2 to the 2k ak minus 1. Which means that I can replace this term by this to the epsilon. Okay. A 1 that comes from here and the epsilon that comes from here. Okay. And this is the recurrence relation that we saw yesterday, right? Is ak is equal to some power of k constant to the k times ak minus 1 to the 1 plus something, right? And if you have a recurrence relation like that, and a0 is small enough, ak goes to 0. Okay. Which is that means that u minus 1 is 0 almost everywhere, u minus 1 plus in the ball of radius 1/2. So done. So this is the first part, L2 to L infinity. Okay. And then the second part is what is the oscillation lemma, right? That says that if you have a bounded solution, now we have bounded solutions. If you have in the unit ball a bounded solution, let's say with oscillation less than 2 or 1, then in a smaller ball, let's say in half the ball, the oscillation decreases a fixed quantity. Okay, so geometrically this is the following, right? Suppose you have a solution that oscillates between minus 1 and 1, so it would be oscillation 2. You can always sort of add a constant. So oscillation 2 corresponds to a function that oscillates in the ball of radius 1 between 0 and 1. It says that it cannot oscillate all the time here up and down, up and down. That there must be some, in the ball of radius 1/2, you should be able to clean a little piece. Okay. So this is the oscillation lemma. Let's say that absolute value of u, that the oscillation of u in the ball of radius 1 is, let's say, 2. In other words, we can normalize it so that the absolute value of u is less or equal than 1. Okay. then the oscillation of u in the ball of radius 1/2 is equal to 2 times lambda, or lambda times 2 for some lambda less than 1 that depends only on ellipticity. Okay? So let me tell you, so let me just do the proof. So the idea is the following. Suppose that V is a subsolution. I'm going to use truncations of U, so it's a subsolution. So let's do U plus. So let's look at U plus, right? And so U plus, I have normalized U to be between -1 and 1. So U plus in the ball of radius 1 is between 0 and 1. Okay. Now, suppose that for some reason I know that U plus restricted to the ball of radius 1/2 or 3/4, right? Suppose that I know that U plus restricted to the ball of radius, let's say 3/4, is very small. It's 0 like almost all of the time, right? It's identically 0 except for a set of measure delta over 2, where delta is the delta of the previous lemma. Okay? Then the previous lemma tells me that restricted to the ball of radius 1/2, U plus is less than 1/2, and I'm done. Okay? Then, I mean, so I have to take delta square, I don't know, but something like that. Then, the previous lemma tells me that the L2 norm of U is very tiny here, so here U goes below 1/2. Right? Remember, very tiny norm L2 means very tiny norm L infinity. Okay? Then U plus restricted to B 1/2 is less than 1/2, and I'm done. Okay? So if I will know that U is 0 sort of in a very, very large chunk of U plus is 0 in a very, very large chunk of B 3/2, well, B 3/4, then in half the ball, U has to get away from the top because of the L2 L infinity estimate. On the other hand, right, now I look at all of U, so it's something that may go up and down, right? And I know that in the ball of radius 3/2, U is at least half of the time above 0 or at least half of the time below 0. Okay? So this is what I need to complete the proof, right? And what I can assume is that U plus is equal to 0 at least half of the time. If not, I look at U minus, right? At least half of the time. Okay? So I have to bridge this gap. I have to go from half of the time to most of the time. Okay? And so basically the idea of the second lemma is the following. The idea of the second lemma is the following. Here I have the level 0. Here I have the level 1. Here I have, let's say, B 1/2, B 3/4. Okay. Then here I have the graph of U. Right. Notice that because of the energy inequality, since U is a subsolution in the ball of radius 1 and is less than 1, the energy is bounded. Right? So note the integral of gradient phi U plus squared, right, is bounded by, I can take a cut of phi, which is 1 in the ball of radius 3/4, right, and this is bounded by u squared, okay, with a cutoff like this. Okay, so the integral of gradient u squared here is bounded, okay, just by the fact that u is between 0 and 1. And I'll use that later with the different truncations, okay? So the idea, keeping this in mind, the idea is the following now. The idea is the following. I have here the graph of u plus, right? And it's going from 0 to 1, 0 to 1. So I'm going to cut at the level 1/2, right? And I say, well, here I have the function u is 0 in a good chunk, at least half of the set, okay? Now, and it's in H1, and its H1 norm is bounded, right? So in order to go from 0 to 1, it needs some space, right? The functions that don't need any space to go from 0 to 1 are the BV functions, where the gradient is in L1, basically. But if the gradient is in L2, you need some room, you know, L2 with finite energy, totally control energy, you need some room to go from 0 to 1, okay? Which means that when I cut at this level, the set of 0 has to grow, okay? If I am above critical, I'm done. If I am below critical, I renormalize this piece. In other words, I double this, right? And I am in the previous situation, exactly in the previous situation, because when I bring this, when I enlarge this by 2, I am between 0 and 1, positive part, all the same, right? So I have to lose another piece of set, okay? And so this indicates that in a finite number of steps, right, I have to cross the critical threshold for the first part of the argument, okay? So let's do that. So in order to do that, let's try to see what is the estimate we can get for a function that is in H1, has H1 norm 1, let's say constant, and is going from 0 to 1. Let's see how much room does it need, okay? So now we forget this is just a matter of H1 and functions between 0 and 1. So let's forget the equation for a minute, okay? So now we have a function w, right, which is in H1. So the integral of gradient w squared is bounded, let's say less or equal than 1, for instance, okay? And w is between 0 and 1. Okay. And I have a set A, the set A where w is identically equal to 0 and has some non-trivial measure. Let me put the 1/2, but it works with any measure you want. Let me put the 1/2, right? And I have the set B, or B are both, D, C. I have the set C, which is the set where W is identically 1. Okay. And I have the intermediate set D. So D is the set where W is strictly between 0 and 1. And I want to get a bound by below on the measure of D in terms of, let's say, the measure of C. I'll fix A to be always measured bigger than 1/2. Okay? Okay? So I want to convince you that to go from 0 to 1, and I need some room, D, right, which is proportional. It has to be related to the size of C, right? Because if C is empty, it's nothing to say. Okay? Okay. So I gave the Sobolev proof, which is in the potential, because this is what I'm going to use now again. Okay, so let me erase that. Just remember that the energy is less than 1, and W is 1 and 0 in some two chunks, right? And so let me make a picture here. I have here the set C, where W is identically 1, and I have here the set A, where W is identically 0. Okay? So I take a point x0 here, and so I have that W is 1, right? And I write this as the integral along each of these segments, right? So this is equal to the integral of WR dr along each of the segments. Okay, and then I integrate along all the segments, so I have here x0, among all the segments that hit A. Okay, so I go do the volume integral along all the segments that hit A. So here what I get is the integral, as I said before, of gradient W dot x0 minus y over x0 minus y to the n, right, integrated on this cone. Okay, so integrated on this cone, which is less than, I will replace it by just everything in a minute. Okay, and here, since I'm integrating along all of these lines instead of the 1, right, I get the measure on the sphere of this cone, right? And the measure on the sphere of this cone is at least the measure of A, right? Because if A is contained in a cone which has measure less than A, the volume is less than A, okay? So here I can put the measure of A is smaller or equal than, and here I put absolute value everywhere and integrate in D. In D. Okay.
I'm sorry, just to
Yes. Go ahead. Go ahead.
So in this, in the setup, you're integrating along these rays, but why aren't we seeing W? So
W is 0 here.
Oh.
So I integrate and is 1 here. So this is okay. Okay. Sorry. Yes, I should have said that. Yeah, I'm going from, in each of these rays, I'm going from 0 to 1. In fact, I integrate until the first time I hit 0. Okay. So I have that the measure of A is less than this integral. And now I integrate on x0 in B. So the measure of A times the measure of B is less or equal than if I integrate here on x0, right? And of course, I change the order of integration. Pardon? C, sorry, C. I know I have to avoid B because it's this. And I change the order of integration. So here I'm integrating y in D, right? And I'm integrating x0 in C. Okay? This goes out of the integral, right? And so among all the sets of the same measure, this is a radial decaying function, right? So this is, let me write it, the integral of gradient W of y, right? On D, the integral of 1 over x0 minus y to the n minus 1 d x0, right? On C. Okay? But this is a radially symmetric decreasing function, right? So among all the sets C of the same measure, right, the integral will be the largest if C is the ball centered at x0. Right? You have a radially symmetric decreasing function, then you can always move what is far away. You know, it's a symmetrization issue. Right? So this integral, right, is smaller or equal than the integral in the ball of radius C to the 1 over n of 1 over r to the n minus 1, right, r to the n minus 1 dr d sigma, right, polar coordinates. So this is C to the 1 over n. So this integral is less or equal than C to the 1 over n, the integral of gradient W in D. And now I have to use H1. Okay? The integral of gradient W in D is smaller or equal than the integral of the H1 norm, the integral of gradient W squared, which we knew it was bounded, right, to the 1/2, times the volume of the domain. To the 1/2. Okay. A, we assume that was bigger than 1/2, so this implies that D to the 1/2 is bigger or equal than C to the 1 minus 1 over n. Okay. So in order to go from 0 to 1, I need this much room. Okay? Okay? And so now, so the important thing is that if C is strictly positive, the amount of room I need is strictly positive. It's not, the exponents are not important, right? The only important thing is that I think when the George did this proof, he was 25 or 26. So the important thing is that V is bigger or equal than C to some C. Okay. Okay, so now let me convince you that with this lemma we can jump the threshold from 1/2 to a small constant, right? So I said, okay, I start with U plus, right? Okay, and the measure of the set where let's say U plus, let's call it U0, right? And has the measure where U0 is equal to 0, right? It is A, which is bigger, A0, which is bigger than 1/2. Okay. Intersection, the ball of radius 3/4, I said, right? Okay, so this is my starting hypothesis. If I am above the threshold, I'm done. If not, I cut at half the way, right? And so here instead of 0 to 1, I'm between 0 and 1/2, but it's the same as before, right? So, okay, so what does it mean if I am, I should say, so I look at, okay, so now I look at the set where U0, so I cut at half and renormalize. Okay, so U1 now is U0 minus 1/2 plus, that is this piece, times 2. Okay. Now I have A1. So now let's look at A1. I'm sorry, I wasn't supposed to go under here. What time is it? Ah, okay. So I have U plus is equal to, I call it U0, right? And I have A0, and I have, which is the set where U0 is equal to 0. I have C0, the set where U0 equal to 1, and okay, C is equal to 0, and okay, and so and I have the set A0. So now I look at U1. So I'm going to look at UK. In fact, UK is going to be U0 minus 1 minus 2 to the minus k, right? So I'm going to cut diagonally like this, plus over 2 to the minus k. Okay, so these UKs, right, are the different slices, right? I cut, I subtract, so I bring the graph to 0, and then I multiply by the width of the strip to make it go from 0 to 1. Okay, so these are all subsolutions that go from 0 to 1, and therefore they all have, by the energy inequality, their energy in the ball of radius through 3/4 is bounded by the same constant. Okay, because they are all subsolutions between 0 and 1 in the ball of radius 1. So the energy of UK in the ball of radius 3/4 is always so equal than constant. Okay. And now I start cutting, right? If in some level of my cutting I want to go through the threshold, then I am done. Okay? If after a finite under control, right? Control number of steps. I go through the threshold, I am done. Okay. What does it mean to go through the threshold? Okay. It means that this set is small enough. Okay. So to go through the threshold for the value k0, varies a little bit more. Threshold for k0 means that the set, the trace of the graph is small. Okay? But the trace of the graph in each step, right? The trace of the graph in each step, I can use it as the C set for the previous cutoff. Right? Because in the previous thing I have 0, 1/2 after renormalization, and something in between. Right? So if the trace on the graph does not go through the threshold, right, then at each step the d is non-trivial, which means that I gain in each step a fixed amount of zero set. Let me write that. Okay. The trace of the graph in each step I can use as the C set for the previous truncation. Right? Let me make a big picture here so I try to convince you. So here I have 0, 1, let's say I have the truncation 1/2, I have the truncation 1/4, right? So here I have a set like this. In the truncation 1/2, right, I have this, and okay, if this threshold if this goes below the threshold after renormalization, then my solution stays half the way, right? If I went below the threshold, I just went up half the way, so I'm done. But if I did not go through the threshold, right, then I can apply the previous lemma to the W, which is 0 here, 1 here, right, after renormalization, and 0 here again, right? Okay, and then the previous lemma says that if this, that is, if the measure of C was non-trivial, then the measure that I need to go from here to here is also non-trivial, right? So as long as I do not go through the threshold, in every step I gain a fixed chunk of zero set, which means that in a finite number of steps under control, I have to go through the threshold, okay? Okay, and that completes the proof, because I started here with measure 1/2, and after a finite number of steps, I get that this strip has to be clean in the ball of radius 1/2. Okay? Okay, just let me say in 2 minutes, right? I like to see the Di Giorgi proof, sort of geometrically, you can think of it in the following way, right? Think, for instance, in the case of a minimal surface equation, the minimal surface equation, when you know that the gradient is bounded, that implies that it's uniformly elliptic, okay? So, so I like to think it in the following way. Suppose, for instance, that you have a solution of a problem which is Lipschitz, right? Lipschitz with constant 1, okay? So suppose that you know that U is Lipschitz with constant 1. Okay. Okay. That means, what does it mean that the surface is Lipschitz? It means that if you slide the surface up at anything below 45 degrees, right, the new surface is above the old one. Okay, so I have sort of a cone of directions, which if the Lipschitz norm is 1, such that if I translate in any of these directions, right, the new graph is above the old one. Okay. The problem is that, you know, these are become critical directions. If I slide at exactly 45 degrees, I could be sticking to the solution. Okay. Now, if I slide to the right or to the left in one of both directions, in measure the graphs have to separate. right? In this picture, both directions are good. If I slide, for instance, exactly at 45 degrees to the right, then the graphs separate here. Okay. So u1 minus u2, u tau minus u, okay, is not only positive, but in measure it is of order the translation. That is, somewhere it is of order the translation. So this is not only positive anymore for any admissible translation tau, right? But for instance, in this graph, for this critical translation, in measure is strictly positive, right? So in measure, u tau minus u, if the translation is of order delta, is bigger than delta in sort of a good chunk of the set. Okay? Say 1/2. Okay? Now, the critical case, in fact, is when the solution is exactly a plane, right? If the solution is exactly a plane, then if you translate into this direction, you don't separate at all. But in that case, you can translate in this direction and you separate a lot. Okay? The Georgi theorem says, it says something about the derivative, and these are basically the derivative, right? Up to a constant, this is a translation, right? An incremental quotient, right? So the Georgi theorem basically says that if there is this separation in measure, right, in half the ball, the separation is uniform, right? So in half the ball, this picture is wrong. So you have this cone of directions on which the function was monotone, and if you go to half the cone, then you can enlarge a little bit your cone. Okay? And so this is the C1 alpha of the solution. You have a Lipschitz solution. This iterative argument tells you that the solution is C1 alpha. Okay? And this is what ellipticity is about. Ellipticity is the ability of the solution to perceive a perturbation that happens somewhere, right? This perturbation here is happening somewhere, you don't know where, but in half the domain, the solution feels the perturbation uniformly. Okay? Okay, let me stop here and I keep going tomorrow.